Welcome to Moreauknows. Today we're going to be learning about water potential. Water potential is kind of what it sounds like. It's the potential energy of water per unit area compared to pure water. So we will be able to figure out where water is going to flow due to osmosis, gravity, pressure, and surface tension. So how do you know when water will move into a cell? Well, we're going to figure this out through a pretty simple equation. So this is the water potential equation, and we use this symbol, and it's called psi, and PSI. And what I like to think of, just a little quick reminder, is that Poseidon was the Greek god of water, and he used to carry around a trident, which looks very similar to the symbol right here. So this equation basically means the water potential is equal to the solute potential and pressure potential added together. So that's going to be our equation that we're going to deal with and we'll be looking at for the next few slides. So what does this mean? Well, if you guys remember osmosis, osmosis is the movement of water from a high concentration of water to a low concentration of water. Well, here you have a slug, and if you were to pour some salt on this slug, the slug would die, and this would be a very, very cruel thing to do, so students don't do this. So if you do this, the water will actually move out of the cell and into the salt concentrated area, and this will happen through osmosis. What's going on chemically when we pour the salt onto a slug, which we should never do? Well, the salt is an ionic bond, has an ionic bond, and when we put it with water, the salt crystal will actually break apart into your chlorine and sodium ions. And so the sodium ions will attract the negative ends of the oxygen, and the chlorine ions, because they carry a negative charge, will attract the hydrogen ends of the water. And so all of this water will start to move in this direction. And it does this because the water starts to become attracted to the chlorine and the sodium ions. And when it does that, it leaves these big open spaces, okay, and I'm just pointing out a few, but it really does leave all these open spaces around the salt ions. And because that space isn't filled, more water will start to flow in, okay? And so that way, if this was the slug, all of its cells that were in contact with the salt would lose water. We're going to measure water potential in something called bars. And water will always flow from a high concentration to a low concentration. And so I've always told my students that it's like going down a slide. And so if you had a slide, then you are always going to move from a high concentration to a low concentration. So if we had a beaker, and this beaker was filled with distilled water, this distilled water would equal 0 bars. Okay? And 0 bars means that it has no solutes in it, and it is exerting no pressure on it. And so if 0 bars were actually poured into or near this tree, water would be absorbed into the tree. Now, how does this happen? Well, there are a bunch of salts that are in the roots. And so the roots will actually absorb water because there's going to be more solutes into the root cells, and so water will actually move in to the roots to try to balance out the cells. And in the stems, there's even more salts in the cells. And so the water from the roots will actually move to the stems, and then also to the leaves, and to then the atmosphere, where we actually really have no water being trapped in a cell. And so this will actually move from a high concentration of water to a low concentration of water. So water will actually move from a high concentration of water to a low concentration of water, or from a high water potential to a low water potential. So let's look at this equation. So here we have our water potential, and this is going to equal our pressure potential. And so our pressure potential is going to be the amount of squeezing that a cell will actually take on. The solute potential is going to be the amount of things that we have inside the liquid. And so this number will actually decrease as we add solutes. So let's think about dropping in just one crystal of salt, so one sodium and chloride. And this was actually going to create water to move in. And so if water moves in, this is going to decrease our water potential. The more water that moves in, the less the solute potential. So if we add more solutes in here, okay, and I'm just going to draw a few in here. So if we have more salts, this is going to really lower the solute potential. So let's say it's about -5 bars. And this is psi s. The pressure potential, this has to do with the amount of physical squeezing. And so normally if water keeps moving into a cell, the cell will burst. But let's say this is a plant cell, like we have here. See, I've got this green wall here. Well, this plant cell is going to allow water to come in, but it's also going to be squeezing back into the center of the cell for every time that there's pressure moving out. And so this cell wall will actually start to push in. And so that's going to create a pressure inside the cell. And this will actually be a positive number. And so psi for pressure can actually equal a positive number, or a +2 bars. And so if we were trying to figure out the water potential for this solution and cell, it would be -3 bars. See how easy that is? Now, sometimes they want us to do some more calculations with our solute potential. So when we're dealing with solute potential, we're going to use this equation right here. And this is going to be called the solute potential equation. This is going to be given on your AP exam, so you don't really have to memorize this. But the equation is going to be -I CRT. And so I is going to stand for the ionization constant. Now this is just a number, so it has no units associated with it. So if you remember back to our previous examples, we had something called salt. And salt is bound by an ionic bond. And because of that, when we add one molecule of salt into a solution, it's like adding a molecule of sodium and a molecule of chlorine. And so if we were to add 1 mole of salt into a liquid, we'd actually be adding 1 mole of sodium and 1 mole of chlorine. And so we have to multiply that by 2. With sucrose, it's a different story. Sucrose is covalently bonded and is a disaccharide, which means it has 2 sugars. And so when it's placed in water, it doesn't dissociate. And so we only give it a unit of 1, or a number of 1. Now the concentration is going to be in moles per liters, which if you take in chemistry means that it's in molarity. And so usually we have some concentration of like 0.2 molars, and that's a capital M, not moles like down here. Okay? R is actually going to be equal to pressure, and this is going to be in terms of liters times bars over moles per kelvins. And this is going to be a constant number. So it's 0.0831. Okay? And this is going to stay the same every problem that you have to do, so you really don't have to worry about it or memorize it. Now, temperature is going to be in kelvins. So how do we figure out what kelvins are? We have to take 273, and then we have to add that to whatever degrees Celsius that we're given in the problem or that you take in your lab. Okay? And then we just multiply those all together, make sure that that negative's on the outside, and you've found psi s. Let's look at our first equation. And so here I've given you guys a cheat sheet that is going to be on your calculation sheet for the AP test. And so our first question says, the molar concentration of a sugar solution in an open beaker has been determined to be 0.2 molars. Calculate the solute potential at 22 degrees Celsius. So, seems like very little to come up with an entire equation that has 4 units needed. So, psi s is going to be equal to negative I CRT. Take a second to try and figure out the equation and answer the question. We are going to need the solute potential of the solution equation. And that's going to be psi s equals negative I CRT. The only reason I knew that was because it asked me to calculate the solute potential. So now we need to find each one of these numbers. And so I is going to be the ionization constant. Well, usually they're going to be between 1 and 2, and sometimes even just 1 themselves. So the ionization constant is going to be based on what is being placed in the solution. And so this is going to be sugar. Because sugar is covalently bonded, it does not dissociate. And so because of that, it's going to be just a number 1. Now, for C, we need to find the concentration. Well, it says that our concentration of sugar has been determined. And so that is 0.2 molars. So that one was pretty easy. Then R. How do we find R? Well, R is a constant, so we can just look. Sorry, let me draw my arrow a little better. So we can just look at our cheat sheet and figure out that it is 0.0831 liters per bars over moles per kelvins. And then we have 1 left to figure out. Well, we need to find temperature, but it needs to be in kelvins. So how do we do that? Well, we take 22 degrees Celsius and convert that into kelvins by adding 273, and then do the math. And so the math, negative 4.9.29 bars. And so to figure out what decimal place I need to estimate this to, I need to look at significant figures. And you really need to look at significant figures if you don't know what they are. And so for here, I've got 0.2 molars. And so 0.2 molars is going to just be one significant figure. So I would need to round this to one place. So that's going to equal 5 bars. Well, what if they ask you, well, what is the overall water potential? How are you going to figure that out? Well, it says that the molar concentration of a sugar solution is in an open beaker. And so if open beaker means that there's no pressure being added to it, we can just figure out that the psi p is going to be 0. So no pressure. And therefore, the answer for the overall water potential will be -5. Thank you for watching Moreauknows. Now you do.